Hello everyone. Today I'm gonna talk about calibration-based differentiable timing optimization in nonlinear global placement. First, a little bit introduction and motivation. I believe everyone knows timing-driven placement, or TDP for short, is crucial for design closure. And there has been many TDP global placement algorithms, including net weighting, net length constraining, mathematical programming, and the differentiable timing optimization. And among all those approaches, differentiable timing optimization, or DTO for short, is considered the state of the art, demonstrating excellent effectiveness with reasonable efficiency. However, there has been only limited discussion on supporting timing exceptions and the advanced timing analysis features in DTO, which hurts its applicability to real industry designs. Common timing exceptions includes clock domain crossing for paths that have different long chain capture clocks, multi-cycle paths that can be finished in multiple clock cycles, false paths for paths that are topological exist but do not need to be timed, and also path segmentation for internal paths that specified by the users. And we also have common path missing removal, or CPPR, to eliminate the on-chip variation path missing on clock networks. So the standard method to support timing exceptions and CPPR in STA is called the tag-based STA. Different from the basic STA, where each timing node only maintains a single actual arrival time AAT, required arrival time RAT, and slack. In tag-based STA, each timing node maintains multiple such AAT, RAT, slack tuples with different tags. And here, different tags represent the timing quantities coming from different timing exceptions, CPPR, transition types, and process corners. Timing quantities coming from different tags are propagated separately. Here I list some tag statistics of an industry design. So in the basic case, there's no timing exceptions, then each timing node only contains a single tag. However, when we start to consider timing exceptions, CPPR, etc., then we end up with about 8 tags per timing node. So one obvious way to support those timing exceptions and CPPR in differentiable timing optimization is to apply the same tagging mechanism here. However, this will oftentimes lead to intractable development and maintenance efforts because this will make the DTO maybe as complex as a sign-off timer, for example. This also leads to unacceptable runtime and memory overhead due to the large amount of tags. This slide summarizes our contributions. We propose a timing calibration technique that can correlate a simple timer to a reference timer, and the calibrated simple timer is ultra-fast and timing exception CPPR aware. We implement a nonlinear differentiable timing-driven global placement framework by extending the calibrated simple timer to a differentiable timing engine. And we propose an angle-based cost weighting scheme that dynamically balancing various optimization objectives, leading to substantial improvement in solution quality and numerical convergence. We propose several techniques that notably reduce runtime while maintaining good solution quality. The proposed framework outperforms the latest Vivado in many key metrics, including Fmax, wireless, routability, backend runtime on a set of industry designs. However, due to time limit, in this talk, we're only focusing on the timing calibration part and some of the experimental results. There are two key concepts in our proposed framework: simple timer ST and reference timer RT. Simple timer is an ultra-fast timer that only supports basic timing propagations, so it doesn't support anything like timing exceptions or CPPR. On the other hand, reference timer is an accurate but might be slow timer. For example, it could be a sign-off timer. And it should support all those advanced STA features like time exception handling and CPPR. The key idea here is that we only optimize placement using this simple timer because it's ultra fast. And we occasionally calibrate this simple timer using reference timer for accuracy, for example, to make it time exception and CPPR aware. Now let's define our timing calibration problem. The inputs include the timing graph, a simple timer, and a reference timer. And we also need to know the arc delay in the simple timer and the worst slack of all the timing nodes in the reference timer. And the outputs are required arrival time of all the endpoints in the simple timer and the delay correction or delta delay of all the timing arcs in the simple timer. The goal here is to exactly matching slacks in the simple timer to the slacks from the reference timer for all the timing nodes when we use the corrected arc delay or delay plus delta delay to propagate timing in the simple timer. Let me use this simple example to walk you through our timing calibration algorithm. The first step is to annotate the timing arc delays in the simple timer. And then we initialize the AATs of all the start points to 0, and then forward propagate the AATs to the other node. Here we simply propagate the setup times. And after that, we annotate the slacks from the reference timer. And then we start a backward propagation procedure to compute RATs and the delta delays using these two equations to match the slacks in the simple timer and the slacks coming from reference timer. Due to the time limit, please refer to my paper to see where these two equations come from and why they work. Here, I just want to give you some sense why this timing calibration algorithm work. If you look at the timing node C, its arrival time is actually coming from BC instead of AC in the simple timer, right? Because BC has delay of 2 and AC has delay of 1. That means if timing node C is timing critical, then based on the simple timer, we should optimize BC over AC. However, if you look at the reference timer, it tells you the opposite, right? Because A has a slack of -2 and B has a slack of -1. That means AC is actually more timing critical in the reference timer. And actually, our timing calibration algorithm can automatically capture that by increasing the delay between AC by 1 and decreasing the delay between BC by 1, and which makes the calibrated the connection between AC more timing critical in the calibrated simple timer. Hopefully this makes sense. And after all those calibration procedure, actually we only need to keep 3 things. The AATs of all the start points, which are 0, the RATs of all the endpoints, and the delta delays of all the timing arcs. And after placement changes, right, we just need to simply plug in the corresponding arc delays in the simple timer and use this delta delay to do the timing correction to approximate the behavior of the reference timer. There are 3 intriguing properties of the calibrated simple timer. The first one is the calibrated simple timer can exactly match the slacks from the reference timer at the placement where the calibration is conducted. And the second one is the slack discrepancy between the calibrated simple timer and the reference timer is bounded by the displacement to the power of p. This displacement is defined with respect to the placement where the last timing calibration is conducted. And the p is related to the war delay model. For example, it is 1 for linear delay models and 2 for quadratic delay models. And property 3 is many placement invariant or insensitive timing factors can be captured through the calibration process. Actually, this property 3 is the key of the lightweightness of the calibrated simple timer, because there are many sources of inaccuracy in simple timer are placement invariant or insensitive. For example, intra-instance delays in GP, multi-cycle pass, and CPPR. And by the virtue of property 3, these placement insensitive or invariant timing factors, actually we don't even need to model them in the simple timer, as they can all be captured by the calibration process automatically. We implement the proposed framework on top of our previous work, ELF-place, and the whole framework is carefully parallelized using CPP test flow. We integrate the global placement engine into the latest AMD Vivado 2023.2 and evaluated it using 150 industry designs on the latest 7nm Versal architecture. And as you can see on the right-hand side, we have some fairly big and complex design in this suite to demonstrate the effectiveness and efficiency of our proposed approach. We compare our proposed global placement engine to the latest Vivado and also our own implementation of net weighting based on DreamPlace 4 and AMF Placer 2. All those three runs, they only differ by global placement, and the rest of the flow are all based on Vivado. As can be seen on the right-hand side, our approach outperforms the other two on almost every single metrics. More specifically, we are about 7 to 9% better on Fmax after GP, and 1 to 3% better after route. And we're also achieving about 7 to 9% better post-route wire length, which translated to much better routability and lead to 5 to 9% the whole backend runtime reduction. And this better routability also leads to more designs to be routable. This slide illustrates how timing calibration looks like during the convergence of GP. Here we call timing calibration every 10 GP iterations. So at iteration 0, 10, 20, 30, and 40, we have 0 slack errors. And between calibrations, we can see the maximum WS error is still bounded by 8%, and the TNS max error is bounded by 2%. Here are the conclusions. In this talk, we propose a timing calibration technique that correlates a simple timer to a reference timer. And the simple timer can effectively handle timing exceptions and the CPPR by periodic calibration. We extended the calibrated simple timer to a differentiable timing optimization engine in global placement, and the proposed framework outperforms the latest Vivado in key metrics including Fmax, wire length, routability, and backend runtime on a set of industry designs.